so far we have been discussing problems in unidirectional transport, and all of the problems we discussed so far used similarity transforms. Okay. That is, either it was transport into an infinite medium, in which case there was no length scale in the problem. Therefore, for the unsteady transport, the only length scale that could be used to scale the coordinate is the ratio of z and root of the diffusivity times time. Okay. So, that was one class of problems. The other class of problems was where there was a length scale, but the height itself was a function of time, and if I scaled the coordinate by the height, okay, for diffusion into a medium of finite extent, I got a similarity transform. I got the equation only in terms of the similarity variable, ratio of z and height in the case of problems with a time dependent height. Now, we will proceed to examine how to solve problems where we do have a bounded domain. Okay. So, there is a length scale in the problem, okay, because we have a bounded domain, that is a domain of finite extent. Okay. How do we solve problems in a domain of finite extent? Okay. So, let us consider the simplest case. Okay. This is the x coordinate and this perpendicular is the z coordinate. Okay. So, you have a bounded domain of height h. Okay. Here t is equal to t naught on the surface. Okay. T is equal to t 1, okay, okay, for t greater than 0, okay, and the temperature T is equal to T naught at T is equal to 0 throughout the domain. So, let me explain the configuration a little bit. I have a medium of height h between two surfaces. Initially, both surfaces and the medium are at a temperature T naught. At time t is equal to 0, the temperature at the bottom surface is instantaneously increased to T1, okay, and because of that the temperature has to increase. Okay. So, you would expect that initially the temperature is T naught everywhere, and at time t is equal to 0 it is increased to a value T1, okay, and as time progresses you would expect the temperature to increase like this, okay, until in the long time limit you would expect a linear temperature profile between these two, okay, provided there are no sources or sinks inside. Okay. And so, as time increases the temperature profile changes between these two plates. Okay. So, the equations, boundary conditions, initial conditions. Okay. Equation, unsteady equation. So, first things first, I will define a scale temperature is equal to T minus T naught by T1 minus T naught. Okay. In this case, I can define a scale temperature, scaled height Z star is equal to Z by H. Okay. I can define the scaled height, that is Z star is equal to Z by H. Okay. So, I cannot use a similarity variable. Okay. In terms of this scale temperature, okay, so the in terms of the dimensional temperature, partial T by partial T is equal to alpha d square T by dz square. Unsteady heat conduction equation. If I substitute T is equal to T star times T1 minus T naught plus T naught, okay, from this equation, okay, I will get the same equation because the scaling of temperature on both sides cancels out, and I will get this same temperature in terms of T star. Okay. The boundary condition, T star is equal to 0 at Z star equals 1. So, here T is equal to T naught means T star is equal to 0. Okay. So, this location is Z is equal to 0, sorry, and this is z equals h, okay, z equals the height h. Okay. In terms of the scaled coordinate, this lower z star is equal to 0 because z star is equal to z by h, and here z star equals 1, okay. Z star is equal to 1, okay, or at, okay, which is the same as z is equal to h, okay. And t star at the bottom surface is equal to 1, okay, at z star is equal to 0, t star is equal to 1, okay. And the initial condition t star is equal to 0 at time t equal to 0, okay. T star is equal to 0 at time t is equal to 0 throughout the medium, because the heating has just been switched on. Therefore, only the bottom surface is at temperature T1. The rest of the medium is at temperature T0, which means that t star is equal to 0 at t equal to 0 for z greater than 0. Okay. So, these are the initial and the boundary conditions. Okay. So, we scaled z star as z by h, okay. We have scaled z star as z by h, okay. I can substitute that into the equation, okay. Partial t star by partial t is equal to alpha, z star is z by h, so therefore, z is equal to h times z star, okay. So, this will be alpha by h square partial square t star by partial z star square. And now this factor can be used for scaling time, okay, because the if I divide throughout by h square by alpha, okay, if I divide throughout by h square by alpha, I will get partial t star by partial t into alpha by h square, okay. So, or rather I should write it better. Okay, on the right hand side is dimensionless, okay, the right side is dimensionless. On the left side the numerator is dimensionless, that means that this product, okay, of t times this also has to be dimensionless, okay, and that is easily verified, okay. I can define the dimensionless time as t star is equal to t alpha by h square, okay. Alpha has dimensions of length square per time divided by h square, length square dimension, times t, which is time. You can verify that that is dimensionless, okay. Okay. So, therefore, my equation becomes that is the equation, okay, and these are the boundary conditions, okay. And you can see that defined in this way by just by scaling, it turns out neither the equations nor the boundary conditions have any parameters in them. Equation has no parameter, the diffusion coefficient has been scaled out. Boundary conditions are at z star is equal to 1, z star equal to 0, t star equals 1 or t star equals 0. Okay. So, expressed in terms of z star, t star and capital T star, the temperature scale temperature, the solutions are universal. Okay. Okay. When expressed in terms of the original variables, of course, they will depend upon parameters, but when expressed in terms of the scaled variables, the temperature profiles that you get are universal. Okay. So, this is the equation that has to be solved. Okay. How do we solve this? Okay. First things, in the limit as t goes to infinity, as for long time, the temperature has to get to this some steady value. Okay. In the limit as t goes to infinity, the temperature has to reach some steady value. Okay. That steady value of course has to be a linear temperature profile between T1 and T0. Okay. So, for the steady I can express the temperature as the sum of a steady part plus a transient part. Okay. The steady part is the temperature in the limit as time goes to infinity. Okay. In the limit as time goes to infinity, the temperature is the steady temperature. Okay. The transient part is the difference between the instantaneous temperature and the steady temperature. Okay. So, the transient part of the temperature is the difference between the instantaneous and the steady temperature. I can substitute this into the conservation equation, okay, and I will get two equations. Okay. So, for the steady part in the long time limit, there is no time dependence. Okay. So, therefore, the equation just reduces to d square t steady by dz square is equal to 0. In the long time limit, you reach a steady temperature which is independent of time. Okay. So, therefore, the time derivative goes to 0. Okay. And the boundary conditions are, okay, Ts is equal to 1 at z star is equal to 0 and Ts is equal to 0 at z star is equal to 1. Okay. So, these are the two boundary conditions. And second order differential equation, this just implies that Ts is equal to some constant z plus some other constant. Okay. It is a linear function. Okay. And you can determine the constants from the boundary conditions, and quite easily you will see that Ts star is equal to 1 minus z star. This is the linear function that is 1 at z star equal to 0 and it is 0 at z star equals 1 for this particular case. Okay. So, that is the steady profile. In the limit as t goes to infinity, this is the steady profile. The transient part of the profile has to decrease to 0 in the limit as time goes to infinity, because the temperature has to converge to the steady profile in the limit as t goes to infinity. Okay. So, now we have derived the steady part, we will derive equation and boundary conditions for the transient part. Okay. So, the total temperature I have written it as a sum of a steady plus a transient part. Okay. We know that partial of T steady plus T transient by partial T is equal to alpha partial square T steady, sorry, there is no alpha here, I have scaled it out, by partial z star square plus partial square T transient by partial z star square. Okay. We know that the time derivative of the steady part is equal to 0. Okay. The time derivative of the steady part is equal to 0, and we also know that we have just solved this condition for the transient, for the steady part, d square T s by dz square is equal to 0. So, this is also equal to 0. Okay. And the equation reduces to partial T transient by partial T is equal to d square, I am sorry, there should be scale time here, okay, d square T transient by partial z star square. Okay. So, that is equation. Okay. Boundary conditions, okay, at z star is equal to 0, T star is equal to 1. Okay. That is, the temperature is 1 at z star is equal to 0. Okay. T star is equal to 1 at z star is equal to 0. Okay. Which means that, okay, the steady temperature is also equal to 1. Okay. The steady temperature is also equal to 1, because that is what we have used to solve this equation. Okay. The steady temperature is 1 at z star is equal to 0, okay, which means that the transient part of the temperature which implies that the transient part, the temperature is equal to 0. Okay, because the transient part is the difference between the total temperature and the steady temperature. So, the transient part is equal to 0. Okay. at z star is equal to 1, the temperature is equal to 0, the steady part of the temperature is also equal to 0. Okay. Note that the total temperature is equal to 0 at time t star at z star is equal to 1, the steady temperature is also equal to 0. Okay. And this would imply that the transient part of the temperature is equal to 0. Okay. And at initial time, the total temperature is equal to 0. Okay. At initial time, just before you increase the temperature of the bottom, the total temperature is equal to 0. The steady temperature is equal to, it is independent of time. Okay. The steady temperature is independent of time, therefore, this is equal to 1 minus z star. And what that implies is that the transient part of the temperature is equal to minus of one minus z star. Okay. So, these are the boundary and initial conditions that are to be used to solve this problem. Okay. Note that the boundary conditions are homogeneous in the sense that the transient part of the temperature is 0 on both walls, on both surfaces, both at z is equal to 0 and z is equal to 1. The transient part of the temperature is equal to 0. Transient part of the temperature is non-zero only at the initial condition T star is equal to 0. Okay. So, that forcing for the transient part is only at initial time. Okay. If it is 0 at initial time and at both boundaries, then the solution is trivial. The transient part of the temperature is equal to 0 everywhere and for all time. But because the transient part of the temperature is non-zero at time t equal to 0, therefore, you have a non-trivial solution. So, the forcing for the transient part of the temperature is at time t equal to 0. Okay. Okay. So, how do we solve this equation? Okay. We use a method called separation of variables. Okay, we use a method called separation of variables. Okay. Separate out the transient part, okay, into two functions, one of which depends only upon z and the other which depends only upon time. Okay. G of t star which depends only on time times capital Z of z star, okay, which depends only on z, okay, and substitute into the equation. Into the governing equation here. So, I will get, so on the left side there is a time derivative. So, I will get z of z star times dg by dt. Okay. On the right side there is a second spatial derivative. So, g will come out times d square capital Z by dz star square, and this should be the scale temperature. Okay. So, this is the equation. And then I divide throughout by g times z, okay, divide the equation throughout by g times z, okay, and it reduces to 1 over g dg by dt star is equal to 1 over z d square z by dz star square. You can see that the left side of the equation depends only upon g, upon time, and the right side of the equation depends only upon z. Okay, the left side of the equation depends only upon time and the right side of the equation depends only upon z. Therefore, both sides of the equation have to be equal to constants, because if this equation is valid for some particular value of time and some particular value of z star. Okay. If this equation is valued for t star and z star, some particular value of t star and somewhat particular value of z star, and the left and the right sides are not constants, they are varying, then I can keep T star the same and change Z star, and then only the right side will change and the left side will not change, because I have kept T star a constant and changed Z star. So, only the right side will change, the left side does not change, and the equation is no longer valid. This equation is for the temperature field. It has to be valid for all values of T star and all values of Z star, and that can happen only if the left and the right sides are both equal to constants. What should that constant be? Okay. So, can it be a positive or a negative constant? Okay. If you take the left side of the equation, okay, 1 by g dg by d star T star is equal to some constant k. Okay. This implies that you can quite easily integrate this. Log g is equal to k log t, that means g is equal to e power k constant, okay, some c e power k times t star. Okay. So, you get an exponential function for g as a function of time. We know that the transient part has to decrease to 0 in the limit of long time limit, because T the solution for the total temperature has to be equal to the solution for the steady temperature in the limit as T goes to infinity. Okay. This implies that the exponential has to be a decreasing exponential function, and therefore, k has to be a constant, a negative constant. Okay. So that the temperature, transient part of the temperature decreases to 0 in the long time limit only if this constant k is a negative constant. Okay. Therefore, this has to be of the form minus some constant minus some number square, where beta is a number. Minus of beta square is a negative constant. Only if it is negative, in the limit as t goes to infinity, this function g will exponentially decrease, okay, to 0, so that the transient part of the temperature decreases to 0. Okay. So, that is the expression for the right and the left sides. Both have to be equal to a constant, and the transient temperature decreases to 0 only if this is equal to a negative constant. Okay. So, solving this part of the equation, one by z d square z by dz star square is equal to minus beta square. Okay. Okay. So, I can multiply left, right and left hand sides by z. Okay. Okay. And the solution is z is equal to a cos of beta z star plus b sine of beta z star. And these are determined from the boundary conditions. Recall, I told you that the boundary conditions are homogeneous. Okay. T star is equal to 0 at z star is equal to 0, and since the only z dependent part of T star, the transient temperature, is z star, this implies that capital Z is also equal to 0. Okay. And the transient part of the temperature is also equal to 0 at z star is equal to 1. Okay. This also implies z is equal to 0. Okay. So, just to make it convenient, consistent, I will just write this as sine and cos. So, the first condition, T star transient temperature is equal to 0 at z star is equal to 0 implies that B is equal to 0, okay, because at z star is equal to 0, capital Z is just equal to B. Okay. So, this implies that B equal to 0. Okay. So, then Z becomes equal to just a sine of beta Z. Okay. Condition that it has to be 0 at z star is equal to 1. Okay. This implies that a sine of beta is equal to 0. Okay. If T transient temperature is 0 at z star is equal to 1, this implies that A sin beta equal to 0. If A is equal to 0, you just get a trivial solution. Okay. However, this can be satisfied even for A not equal to 0, provided this beta is equal to some integer times pi. Okay. This I will call this as beta I, okay, is equal to some integer times pi. Okay. You know that sin of 0 is 0. So, for I equal to 0 it is 0, sin pi is 0, 1 is 0, sin 2 pi is 0, etc. Okay. So, beta can have any value, okay, can have value I pi, where I is any integer, okay, integer I. Okay. Okay. Provided I is an integer, the boundary conditions on the two boundaries are satisfied. Okay. Okay. With this, the solution for z that satisfies the boundary condition becomes A sin of I pi z star. Therefore, beta is equal to I times pi. Okay. So, I have solved the first part of this equation, 1 by z d square z by dz star square is equal to minus beta square. The second part of the equation is, okay, 1 by g dg by dt star is equal to minus beta square, which is minus of I pi the whole square. Okay. And this implies that g is equal to e power minus I pi the whole square t star. Okay. Okay, that is the solution for g. Okay. And if we write T transient part of the temperature is equal to Z times G, this becomes A sine of I pi Z star e power minus I square, or let me write it again. Okay. This solution satisfies the governing equation, the differential equation, and the boundary conditions for any value of I. Okay. This satisfies the governing equation and the boundary conditions for any value of I. Okay. So, therefore, the most general solution that satisfies the governing equations and the boundary condition is the summation of this over I is equal to 0 to infinity, okay, of A I times this. So, this solution satisfies the governing equations and the two boundary conditions. There are constants of integration A I in this an infinite series. How do we determine these? We have only the initial condition to determine these constants. Okay. The initial condition is that at T star is equal to 0, okay, the transient part of the temperature is equal to minus the steady part of the temperature, which was minus of 1 minus Z star, okay, is equal to minus of the steady part of the temperature, which is minus of 1 minus Z star. Okay. Therefore, at t equal to 0, the left side is summation over I of A I sine of I pi Z star. Okay. The exponential just becomes 1 at t star is equal to 0, okay, is equal to the right side, which is minus of 1 minus Z star, that is the initial condition. Okay. So, from this equation we have to determine what are the constants A, okay, and once we determine the constants A, then we have the complete temperature field. Okay. So, I will proceed to examine what are the constants A in the next lecture, okay, and complete the solution of this problem. Okay. So, I will see you in the next lecture to complete this separation of variables problem. I will see you then.